Oh, goodness gracious. Oops, oops, oops. Heck. Thank you. No, not that. Oi, oi, oi. Okay, folks, it is that time, so I'm going to go ahead and get started. We do have quite a bit to cover today. So in this section, I am going to be discussing acids, how to name an acid, and the formula of an acid. Then we will move on to formula mass compared to molar mass. After we talk about formula mass and molar mass, which I'll introduce Avogadro's number at that time as well, we'll deal with some stoichiometry involving formulas, elements, Avogadro's number, and then we're going to do a very brief stint on percent composition. So, the first thing I want to make sure that you remember is the material I went over for the majority of today's lecture. Basically, I started off the day with those 4 examples of ionic compounds where you either had to give me the formula or give me the name. That is where the test on Tuesday stops. So everything else, all the naming of covalent molecules, all the formulas of covalent molecules, that will be on exam 3, as will the stuff that I'm going over in lab today. So again, I just wanted to make sure that you remember that. So what we're going to do today is I'm going to start with the information and let's get going. So let's start with acids as soon as I get my marker to work. Before we actually get into an acid, we need to know what an acid is. And there are actually 3 definitions that you will encounter in College Chemistry 1 and College Chemistry 2. But I'm going to basically refer to 2 of them today, and that is the Arrhenius definition and the Bronsted-Lowry definition. And the reason I'm going to introduce both of them is because they are the exact same. In the case of both of these definitions, an acid is a proton donor. Which is often illustrated as an H+. Now, why would we illustrate it as an H+? Well, let's just go back and think about hydrogen. If we have hydrogen atom, it has its proton in the nucleus of the atom, and then in the electron cloud surrounding that nucleus, there is the electron. Now, if we were to allow hydrogen to ionize, what would be left is a proton in the nucleus and absolutely nothing left in the cloud. And therefore, you would have the H+. So it's called a proton. H+ is called a proton often because that's all that's left is the proton itself. So again, an acid is going to be a proton donor. Now, when we think about the inorganic acids, what that means is you take a chemical substance that has an acidic proton and you add that substance to water. Now, what happens is that the hydrogen in that substance is going to get donated to the water, and therefore you wind up making hydronium and the anion that's left over from the acid, which in this case would be the chloride. Now, another way to illustrate this is we can instead use the symbol AQ, which stands for aqueous. Meaning that the substance is dissolved in water. So you will see another way of writing this equation, and that is we could write it as HCl aqueous goes to make H plus aqueous plus Cl minus aqueous. These two equations mean the exact same thing, because in the top equation, we're saying that we are dissolving the HCl in water. In the bottom of equation, we're just saying the HCl is dissolved in water. So they mean the same thing, they just look different because of whether we go ahead and write out the hydronium, which is the true nature of that proton in water, or whether we just illustrate the proton. So again, an acid is going to be a substance that dissolves in water. Now, this comes back to something I said this morning because I knew it was going to come up. Oftentimes, almost every year when I have written out HCl and called it hydrogen chloride, I've had a student raise their hand and go, I thought that was hydrochloric acid. Well, that is where the difference lies. HCl by itself is hydrogen chloride. HCl, once dissolved in water, is hydrochloric acid. So that is how I illustrate whether I'm dealing with just a covalent molecule or whether I'm truly dealing with an acid. Is I incorporate the AQ in parentheses with an acid. So now let's talk about the formula of an acid. When we're talking about the formula of an acid, the number of acidic protons in the formula will equal the charge or the magnitude of the charge on the anion. When we talk about this anion, it doesn't matter whether it's an elemental anion or a polyatomic anion. And once again, you will note that AQ is used to emphasize that it is an acids formula. Okay, so that's formula of an acid. Now let's talk about the name of an acid. The name of an acid depends on the suffix of the ion. Now, again, these are inorganic acids. They are not organic. That's a whole different ballgame. What do I mean by that? So what I mean by that is if the anion ends in IDE, then you're going to use the prefix hydro followed by the root of the anion and ic acid. If the ion ends in ATE, then it's going to be the root of the ion followed by ic acid. But if the anion ends in ITE, then it's going to be the root of the ion followed by us acid. So let's look at some examples. If I have HCl aqueous, well, let me make it into a little bit easier to read. We're going to have the acid formula, from which I am going to determine the anion, from which we're going to get the name of the anion, and then finally we'll get the name of the acid. Okay, so let's start out with HCl aqueous. HCl aqueous has the anion Cl minus. The name of that anion is chloride, so it ends in IDE. Because the anion ends in IDE, that means we're going to use the hydro, followed by the root, which in this case is chlor, and the ending ic acid. So that is hydrochloric acid, as I've already mentioned. For the next one, let's say I have H3N. Well, the anion is the nitrogen, which is in group 15, so it's a 3- charge. That anion is called nitride. Again, we have the ending IDE. Because we have the ending IDE, it's going to be hydro, the root of the name, nitr, followed by ic acid. So that's hydronitric acid. Let's do this one. Let's take H2SO4. H2SO4, the anion is SO4, and it will have a 2- charge because we have 2 hydrogens. SO4 2- is sulfate. So it now ends in ATE. Since it ends in ATE, it's just going to use the root followed by ic acid. So this is sulfuric acid. We can do HC2H3O2 aqueous. The anion is going to be C2H3O2, and it'll be a -1 charge because there is 1 hydrogen. This anion is known as acetate. Because it ends in ATE, that means we're going to wind up calling it by the root with the ending ic acid. So that is acetic acid, which is the major component in vinegar. And then let's do one more. We have HNO2 aqueous. Our anion is NO2, which is a -1 charge. We know that because there's 1 hydrogen there. NO2- is nitrite. Because it ends in ITE, it is going to get us acid. So this becomes nitrous acid. Now we can work backwards too, folks. We don't have to go in the same order all the time. Let's go from the name to the formula. So let's say I have hydrocyanic acid. The first thing I note is that I have a prefix hydro and ic acid. Anytime you have hydro and ic acid, that means that it came from the ide. So this had to come from cyanide. Cyanide is the polyatomic ion Cn minus. And as far as the formula is concerned, it's going to have the same number of hydrogens as the magnitude of the charge. So this will have 1 hydrogen. And then we'll include the aqueous. Let's look at the next one. Perchloric acid. Okay, I don't see a hydro, but I see an ic acid. If you don't have a hydro, but you have an ic acid, that means it came from the 8. So the ion it came from is perchlorate. With the ending AT, perchlorate is ClO4 minus. Because it has a -1 charge, that means it's going to have 1 hydrogen as an acid. And so it'd be HClO4 aqueous. The last one, let's go with hypoiodous acid. Hypo is not hydro. So the prefix doesn't matter. What does matter is the us acid. When it is an us acid, that means it had to come from the ite anion. So this came from hypoiodite, which is IO minus. So the acid is going to be HIO minus because the number, HIO aqueous, because the number of hydrogens is equivalent to the magnitude of the charge. Questions about naming acids? I went left to right and then I went right to left. This is the mental process either direction. Okay, so let me pull up the chat, make sure nobody chats in. So the next thing we're going to go over is formula mass, molar mass, and Avogadro's number. Okay. So the first thing I want to do of this is we're going to talk about this formula mass. We've been talking about formulas. Whether it is the formula of an atom of an element that we discussed a long time ago, whether it is the formula of an ionic compound, whether it is the formula of a covalent molecule, or whether it is the formula of an acid. we've been talking about formulas. Now, before I really get into the formula mass, I want to remind you of something you've already done. Previously, this semester, you determined the average atomic mass of an element. And that average atomic mass was equal to the sum over all naturally occurring isotopes of the isotope mass times the abundance. And we discussed the fact that it is the average atomic mass that appears on the periodic table for an atom of an element. So, for example, if I have oxygen as an element, as a just an atom of an element, oxygen has the formula of O. That's its formula as an atom of an element. Now, if we look up on the periodic table, we will find out that the average atomic mass is 15.9994 AMU. Folks, when we were calculating the average atomic mass, the average atomic mass is the same as the formula mass. Because again, the formula for a single atom of oxygen is O. So it would be 15.9994 AMU. Now, here's the problem with working with AMUs. When you're talking about the atom of an element, we're talking about something that is 1 angstrom in size. 1 angstrom is 1 times 10 to the minus 10 meters across. It is an extremely small diameter object. It is something that we are unable to manipulate as a single object. So, an individual was doing some research. That individual's name is Lorenzo Romano Amadeo Carlo Avogadro di Coen e di Sreto. And I hope I didn't butcher it too bad. Better known as simply Avogadro. And Avogadro, what he discovered is instead of looking at 1 atom of oxygen, if he took and looked at 6.022 times 10 to the 23rd oxygen atoms, then instead of talking about a formula mass of AMUs, he had something he could actually measure. He had 15.9994 grams of oxygen. Now, Avogadro's number, 6.022 times 10 to the 23rd of anything is equal to 1 mole of that thing. Avogadro's number, folks, is a counting number, basically. Just like you say there's 12 eggs to 1 dozen. You physically count the eggs, 12 of them, and that's a dozen. Avogadro's number is also a counting number. It is 6.022 times 10 to the 23rd. And that's equal to a mole. Now, just to give you an idea of what 6.022 times 10 to the 23rd really is, let's take something that is macroscopic. Let's take a little bitty marble. No bigger than a penny type marble. If you were to stack the entire mainland USA 70 feet high in marbles, you would get 6.022 times 10 to the 23rd. That is 10 times plus your height. You got to stack it that high to get 70 feet of marbles. So a mole is a huge number when you're talking about the macroscopic world. But when you're talking about oxygen, whose diameter is 1 times 10 to the minus 10, it's not as big of a it is very difficult to imagine, but at the same time, it's something you can handle. So again, Avogadro found out if you took 6.022 times 10 to the 23rd oxygen atoms, that the mass of that would be 15.9994 grams of oxygen, and that is referred to as 1 mole of oxygen. Now, when you talk about 6.022 times 10 to the 23rd of a thing, what you are doing is you are talking mole and you are talking mass. So that is known as its molar mass. So I've actually incorporated all of these terms already. Formula mass, molar mass. So let's talk. Formula mass is for 1 of whatever. Molar mass is for a mole of whatever, which just happens to be the 6.022 times 10 to the 23rd. We can say the same thing for hydrogen, folks. Let's talk about hydrogen, and let's talk 1 atom of hydrogen. Well, 1 atom of hydrogen is going to have a formula mass of 1.00794 AMU, as found on the periodic table. But if instead we talk about 6.022 times 10 to the 23rd hydrogen atoms, now what we're working with is we're working with the molar mass for hydrogen, which is 1.00794 grams of hydrogen is equal to 1 mole of hydrogen. So in other words, if we talk about an entire Avogadro's number worth of hydrogen, then we get 1.00794 grams of it. Now, formula mass, molar mass, Avogadro's number. Hopefully you have a sense of what those things mean now. Before we move on to the next piece, you've got to also have a sense of the law of conservation of mass. Or of matter. Let's start with matter. Law of conservation of matter basically states that matter cannot be created nor destroyed. Now, what does that mean? It means that if a hydrogen atom is incorporated into, say, water, it will bring its mass with it. And really, folks, this comes back down to the definition of matter. Matter is any object that has mass and takes up space. Hydrogen has mass and takes up space. So if you cannot create nor destroy matter, that means you cannot create nor destroy the hydrogen. And if you cannot create nor destroy the hydrogen, that means you cannot create nor destroy its mass worth of hydrogen. So that comes into when we start getting into our formulas. So let's take hydrogen and water. Hydrogen, there are 2 hydrogens and there is 1 oxygen in water. Hydrogen has a mass of 1.00794 AMUs. Oxygen has a mass of 15.9994 AMU. The hydrogens contribute a total of 2.01588 AMUs to the overall mass. And the oxygen contributes 15.9994 AMUs to the overall mass, giving water 18.01528 AMU. Now it is AMU if we are talking about 1 formula unit of water. But just like our atoms of the elements, if instead of talking about 1, we talk about 6.022 times 10 to the 23rd water molecules, then we're going to be working with its molar mass, which is 18.01528 grams of water is equal to 1 mole of water. The next one, let's take calcium nitrate. Now you got to remember what calcium nitrate is. It's telling you that it has one calcium ion and two nitrate ions. So it has one calcium and it has two nitrogens and it has 6 oxygens within its molecule. The calcium brings with it a mass of 40.078. The nitrogen brings with it a mass of 14.006 and the oxygen 15.9994. So the calcium contributes 40.078 to the overall structure. The nitrogens contribute 28.012 to the overall mass, and the oxygens contribute 95.9964. You add that up and you get 164.0864 AMUs. That would be the mass of one atom, of one molecule. But as we keep going, calcium nitrate, if we're going to talk about 6.022 times 10 to the 23rd calcium nitrate molecules, then we're no longer talking about atomic mass units. Now we're going to be talking in terms of grams. So it's going to be 164.0864 grams of calcium nitrate is equal to 1 mole of calcium nitrate. One last one I want to go over because, well, you got introduced to them last week in lab, and that is the hydrates. And I'm going to go back to the example I gave you in lab where we were working with cobalt chloride hexahydrate. And I even took the time to draw to attempt to draw a crystal. And I was like, okay, there's one COCl2 in the crystal along with 6 water molecules. That's what the formula of the hydrate means. So in our cobalt chloride hexahydrate, we will have 1 cobalt, we will have 2 chlorines, we will have 12 hydrogens, and we will have 6 oxygens. Cobalt has a mass of 58.9331. Chlorine a mass of 35.453. Hydrogen a mass of 1.00794. And oxygen a mass of 15.9994. So our cobalt contributes 58.931 to the overall. The chlorines contribute 70.906 to the overall. The hydrogens contribute 12.09528 to the overall. And the oxygens contribute 95.9964 to the overall. When adding it all together, you get 237.93078 AMUs. And again, that is the mass of one formula unit of our cobalt chloride hexahydrate. I wanted to show you a hydrate because I want to remind you that the dot in the formula of a hydrate does not mean multiplication. And just like before, instead of 1 unit, if we want to talk about 6 units, excuse me, 6, if we want to talk about 6.022 times 10 to the 23rd molecules of COCl2.6 waters, then it would be 237.93078 grams of COCl2.6 waters is equal to 1 mole of COCl2.6 waters. Questions? Let me give you a couple to do real quick. And I'm just going to have you calculate the molar mass. Of Mg3AlOH6Cl and nickel 2 phosphate. To help you out, I will give you the information related to the atoms. Magnesium is 24.305. Aluminum is 26.981. Oxygen 15.9994. Hydrogen is 1.00794. Chlorine is 35.453. And nickel is 58.693. Phosphorus is 30.976. So on the screen, I have the answers to those. For the first one, I added the mass of 3 magnesiums, 1 aluminum, 6 oxygens, 6 hydrogens, and 1 chlorine together to get a mass for this magnesium 3 aluminum layered double hydroxide, which is 237.39304 grams per 1 mole. And then for the nickel 2 phosphate, it was 3 nickels, 2 phosphoruses, and 8 oxygens. When you add those together, you get a molar mass of 366.0262 grams of nickel 2 phosphate is equal to 1 mole of nickel 2 phosphate. Any questions? Okay, so at this point, what I would like to do is take about a let's plan to be back at 3:50, which means you're going to get a 15-minute break. So 3:50, come back, and then we will work our way through the rest of today. Do that and that. And go back to here. Okay. I don't know what that is. We'll just leave it alone. Okay, folks, so the next thing we're going to do is we are going to start working on what is basically what is known as stoichiometry. Which is essentially chemical conversions. Now, I personally think you'll find these conversions a lot simpler than the conversions we did at the start of the semester. And the reason I think you'll find them simpler is because I can easily give you some clues as to what to look for. So that should help tremendously. So, the very first thing when we start getting into these chemical conversions is that I look for is whether the starting substance and ending substance are the same or different. If the starting substance and the ending substance are different, then that is your clue that you are going to need to use a mole to mole ratio during the conversion. Now, there's a couple of different ways to find your mole-to-mole ratio, but we're only going to be talking about one of them today. We've got to wait until we balance chemical equations to get to the other one. But for today, the one we're going to talk about is the mole-to-mole ratio of an atom of an element to the compound. And this is going to come directly from the subscripts of the formula. Now, the second thing that I look for is I look for the unit. And if I see the terms atom, molecules, or ions, then that is my cue to tell me that I am going to be using Avogadro's number. Which again is 6.022 times 10 to the 23rd of anything is equal to 1 mole of that thing. Finally, the thing that I look for is if grams is a unit of interest, or technically other units of mass, it could be kilogram or whatever, but if grams is involved, then that is my cue that I will be needing to use the molar mass for that compound or that element at some point. So this just helps me sort out the possible conversion factors I may have along the way. Now, what I'd rather do, I've given you the gist. Now what we're going to do is I'm going to do a few examples. So, example number 1. How many oxygen atoms are in .65 moles of sodium carbonate? Okay, so back at the beginning of the semester when we were doing dimensional analysis, the first thing I told you to do is to identify what you were given. In this particular case, I am given 2.65 moles of sodium carbonate. That is my starting point. I also told you to identify what you want to solve for. I want oxygen atoms. Now, this is where I'm going to use that number 1, 2, and 3 from above to help me figure out the possible conversion factors I want. The first thing I notice is that my substance is different. It has a different formula. So when your substance is different, it means you're going to need a mole to mole ratio. The mole to mole ratio is going to come from the formula. And basically, by looking at this formula, for every one of those sodium carbonates, or for every 1 mole of sodium carbonate, you have 3 moles of oxygen. The next thing I notice is I notice the term atoms. And I told you, anytime I see the word atoms, molecules, or ions, I am going to go to Avogadro's number. So that would be 1 mole of O is equal to 6.022 times 10 to the 23rd of O. In this case, O atoms. So I have possible conversion factors. Now I'm ready to start the math. Back at the beginning of the semester, when I was doing conversions, I said you're always going to start with a piece of information you've been given. So we're going to start with the 2.65 moles of Na2CO3. Our very first conversion factor is going to have moles of Na2CO3. And the conversion factor that has moles of Na2CO3 is our mole to mole ratio. Now, I have the moles of sodium carbonate in the numerator. So in order for it to cancel out, I will need to place the moles of sodium carbonate in the denominator and the other portion of the mole to mole ratio into the numerator. You had to place the moles of sodium carbonate in the denominator so that the unit and the substance cancels. That is a key piece to stoichiometry. It is not sufficient for the unit to cancel. In stoichiometry, the unit and the substance has to cancel. Now, I have moles of O left over, so I need another conversion factor, and that's where Avogadro's number is going to come in. I have moles of O in the numerator, so I need moles of O in the denominator. That means the other half of Avogadro's number has got to go into the numerator. It had to be in that order to make certain the moles of O would cancel, and now I am left with atoms of O. Now, when you key this into the calculator, you will get 4.79 times 10 to the 24 O atoms as your answer. Questions about that example? I will be doing a couple more. And I'll be using the same process. Identify what I'm starting with, identify what I want to solve for, and then I'm going to be tearing apart those pieces of information to identify my conversion factors. Okay, so let's look at another example. How many molecules of methane are present in 28.165 grams of methane? So we start by identifying what we were given. We were given 28.615 grams of methane. We are then going to identify what we want to solve for. I need molecules of methane. And this is where I start using that 1 through 3 again to figure out what conversion factors I need. So the very first thing I see is that my substance is identical. I don't need to worry about the substance in this case because it's the same substance. So let's look at the other stuff though. So the first thing I spot is grams. Anytime I see grams, that means I'm going to need the molar mass. So I have one carbon at 12.011, and I have 4 hydrogens at 1.00794. The carbon contributes 12.011 to the overall structure, and the hydrogens 4.03176, for a total of 16.04276 grams of methane is equal to 1 mole of methane. The next thing I notice is that I have molecules. And anytime I have molecules, that means I'm going to need Avogadro's number. Which is 1 mole of something, in this case it'll be methane, is equal to 6.022 times 10 to the 23rd of that thing, in this case methane molecules. Now that I've torn this thing apart, I'm ready to start my math. I'm going to start with the piece of information I was given, which was the 28.165 grams of methane. My first conversion factor needs grams of methane, so I will be using the molar mass because it has grams of methane in it. I will put the mass portion in the denominator, so 16.04276 grams of methane to 1 mole of methane. The mass portion had to go in the denominator so that the unit and the substance would cancel, leaving me moles of methane. Now that I have moles of methane, I can use Avogadro's number to get it from moles into molecules. 1 mole of methane of that equality is going to go into the denominator, while the 6.022 times 10 to the 23rd methane molecules goes into the numerator. The moles of methane had to go in the denominator so that the unit and the substance would cancel, leaving me the desired unit of molecules. When you key this into the calculator, the answer that you get is 1.057 times 10 to the 24 methane molecules. Questions about that one? So let's look at one more of these. How many grams of carbon are in 21.926 grams of lead 4 carbonate? I'm going to identify what I was given, which is the 21.926 grams of lead carbonate. And I'm going to identify what I want to solve for. I want to solve for grams of carbon. And now I start tearing this thing apart. The very first thing I notice is that my starting substance and my ending substance are different. Because they are different, that means I'm going to need a mole to mole ratio. Which is going to come from the formula. So for every 1 mole of PbCO3 2 that there will be 2 moles of carbon. The next thing I notice is that I'm going to need grams of lead 2 carbonate. Anytime I see the term grams, that means that I'm going to need to use the molar mass. So I have 1 lead at 207.2. I have 2 carbons at 12.011 each, and I have 6 oxygens at 15.9994. So the lead contributes 207.2. The carbon contributes 24.022, and the oxygens contribute 95.9964. So the molar mass of the lead 2 carbonate is going to be 327.2184 grams of PbCO32 is equal to 1 mole of PbCO32. Continuing on, the next thing I notice is that I need grams again. Anytime I need grams, that means I've got to have the molar mass. Keep doing that. So I need the molar mass of carbon, which according to the formula, 1 mole of carbon will equal 12.011 grams of carbon. Okay, now that I have my conversion factors, I'm ready to try this. So I start with the 21.926 grams of lead 4 carbonate. My first conversion factor is going to have the lead 4 carbonate in it. So I'll be using the molar mass of lead 4 carbonate, which is 327.2184 grams of lead 4 carbonate is equal to 1 mole of lead 4 carbonate. The grams were placed in the denominator so that the unit and the substance would cancel. My next conversion factor is going to have the moles of lead 4 carbonate. So I'm going to, and once you use a conversion factor, you can't use it again. So I'm not using the molar mass again. So that means I have to use the mole to mole ratio. So 1 mole of PbCO32 is 2 moles of carbon. The PbCO32 was placed in the denominator so that the substance and unit would cancel out, leaving moles of carbon. And now I need to convert that into grams of carbon using carbon's molar mass. I will place the mole portion of carbon's molar mass in the denominator with the grams in the numerator. The mole portion had to be placed in the denominator so that it would cancel. And I am left with grams of carbon. And when I calculate it out, I get 1.6096 grams of carbon. Questions about our first encounter of stoichiometry? We will encounter stoichiometry a lot more before by the third test. We'll start to encounter it more. Definitely by the final, you will be encountering it a lot. And no matter where I do the stoichiometry, I will still use the same mental process over and over and over again. In fact, after fall break, I'm not going to assign this before fall break, but after fall break, there are several videos that I will be assigning. It just gives you more to watch to practice this. They start out really, really simple and they get more complex over time. And then I'm not certain where I was headed with that last thought, but anyhow, oh, and there's like 100 of them. So if it's not clicking and you need more, you'll have a lot more you can use. So since I don't see any questions about this, we're going to go to the last item. And that is going to be the law of definite proportions. Basically, folks, we've already said that our compounds have unique names and formulas. And that if you change the formula, you change the substance. So the law of definite proportions indicates that the proportions, I'm gonna have to move this and charge it. It indicates that the proportions of the atoms within a molecule will always be the same. To illustrate this, what I want to do is, and basically we can illustrate this through percent composition. So to illustrate it, what I want to do is I want to take the compound ammonia. Ammonia by its formula has 1 nitrogen and it has 3 hydrogens. Ammonia will always have 1 nitrogen and 3 hydrogens. It doesn't matter where you get the ammonia, it's always going to be 1 nitrogen and 3 hydrogens. Nitrogen has a mass of 14.006 and hydrogen a mass of 1.00794. The nitrogen contributes 14.006 to the overall structure, and the hydrogens contribute 3.02382 to the overall, giving the mass of our ammonia being 17.02982. Now, if we want to know the percent nitrogen in ammonia, we can take the mass of the nitrogen in the ammonia and divide it by the total mass of ammonia times 100, and we will get 82.3%. No, excuse me, 82.3% nitrogen. We could do the same thing with our hydrogen, our percent hydrogen. It would be equal to the 3.02382 divided by the 17.02982 times 100. And it means that our nitrogen would always be 17. That was supposed to be a 2, I'm sorry. I rounded wrong. 17.8% hydrogen. Now, There are two, I gave you, so basically what this is saying is no matter where you find ammonia, because ammonia is always NH3, and because nitrogen is always 14.006 grams, and hydrogen is always 1.00794 grams, what it means is that no matter where you find the ammonia, 82.2% of the compound is nitrogen. 17.8% of the compound is hydrogen. Now, there is another way we could have gotten the percent hydrogen, and that is to realize that the compound itself, the compound's mass, represents 100%. So we could have gotten the percent hydrogen by taking the 100% and subtracting it from that, the percent nitrogen, or in other words, 100 minus 82.2, and that would have given us the 17.8% that is hydrogen. So folks, what we've been doing is we have been focusing on the mathematics associated with the formulas of the compounds that we have been discussing. After fall break, we're going to come back and we are going to get into the nitty-gritty about what these compounds look like. And we're going to get into Lewis structures. But with that, I am done for today. Unless you have questions. And I'll come right back to the screen, but I'm going to stop recording.